is simultaneous. Okay, mag-record na lang ko through. There is a simultaneous attack of the nucleophile and the living group leaving your substrate. No? And the other one, of course, is the SN1, where once you have your protonated alcohol, it can leave the substrate and you will recover this one, and instead you will get your carbocation. And once you form your carbocation as your intermediate, then the nucleophile can attack your carbocation, and that is for the SN1 reaction. So another property of alcohol is that alcohol have acidities similar to that of water. So for example, water has a pKa value of 15.74. Of course, you know that water is would dissociate also, no? Could have an auto-ionization of water. So the pKa value of ethanol of our alcohol is similar to that of water. So 15.74, the pKa is 15.5 also for water. And the other kind of alcohols, it's close also to water, 1 to 2, 3 carbons. And here you have 1 to 4. Third butyl alcohol, and you have a lower pKa for this, higher pKa and a lower. And so if you remember your SN1, SN2 reactions, chapter introduction, we have already discussed this one. Water, on the relative acidity of alcohol and water, water is more acidic than your alcohol, but alcohol is more acidic than your alkynes. No, of course, there is acidity for your hydrogen here, and it can be deprotonated, can be dissociated. No, there's a slight acidity for that, and this is of course more acidic than the hydrogen, and this one is very less acidic na the ammonia and the alkene. So in this series, you can see that the water rather, and followed by the alcohols are the strongest acids in the series. And here you can see on the increasing acidity, water being stronger acid relative to that of the alcohol. And if you check on the trend of the acidity and basicity with respect to its conjugate base, now the conjugate base of your water is the OH, conjugate base of your ROH is OR, and you have your RC triple bond C. Okay, and so if this is the trend, okay, if water is the strongest acid, then the relative basicity is baliktad, no? Katong pinaka-strongest acid o its conjugate base now be the weakest base. Okay, the stronger your acid, the weaker would be its conjugate base. Okay, you can see in the series here. For example, here this is the weak acid, and its conjugate base R minus become the strongest base, followed by here NH2 hydride. This one, the alkoxide. So the alkoxy group OR is more basic than your OH, no? And again, one reason, if you can just look at on the structure here, you have your alkyl group which would have an electron donating inductive effect. So you expect your oxygen to bear more or partial negative charge, or bear more negative charge, you know, because of the electron inducing inductive effect that would comes from the alkyl group as compared to hydrogen. So meaning if you have an R, it will induce more electron density towards your oxygen, that the negative charge or the basicity of the electrons here coming from oxygen will be enhanced as compared kung hydrogen lang. And how much more if you have your pi bonds, triple bonds, can easily more basic than the OR. So because of the pi bond. Okay, so you have your increasing basicity. Again, the conjugate base would be the least basic for that of the strongest acid. So from the chapter 3, we have learned that the alcohols can be converted into the alkyl halide. Following the substitution reaction, you can actually have your OH be converted to our RX halide, you produce that one. And I remember in that exam that we had, no, very few people were actually able to obtain the right product. No, simply you just have to look on the kind of nucleophile that you will use in order for you to get your product. Of course, if OH will have to be substituted with X, like coming from halide, you expect your agent here to be halides, right? To form this one, you wouldn't expect that you will have, for example, a hydrogen. Okay, so from that, you can have your hydrogen halides like HX, HI, HCl, HBr, and you can substitute that one. So of course, you have your I minus or X minus, Hn halides negative charge, and you can substitute this one following SN1, SN2, SN1 or SN2 kind of reaction. And for bromine, you can always also use PBr3. We have used this kind of reagent before, and can for chlorine you can also use SOCl2. But you can also use HX, not ClBr and iodine, and this one follows the substitution reaction. So we can have an example. You have your OH in the presence of a concentrated HCl, hydrochloric acid. No, and so what do we expect? 25 degrees Celsius. Can, of course, there will be a concentrated one. There is a substitution of the OH substituted with the Cl here. No? Always remember you have your OH, the whole group of atoms relative to the carbon here will become like negative charge, right? And in order for this to leave, of course, we've learned that this one has to be protonated first before it will become a good living group, before it will leave the substrate. So you have here an acid that can be protonated, and then the chloride coming from HCl would then attack your carbocation here, your carbon bearing a partial positive charge if it follows the SN2. This one follows SN1 reaction. So for PBr3, if PBr3 will be our source of bromide, so we can substitute this one with bromide. So another one, alkyl halides are the reactions of alcohol. So you can also have, aside from this one, aside from HCl or PBr3, you can also have your source of halides. General reaction, you have your hydrogen halide, HX. And the product would, the side product or the byproduct would be your water, so HOH. The order of reactivity of alcohols is that 3 degree is much higher, is much reactive than 2 degree, than 1 degree, and metal is very less reactive for this kind of reaction. And what would be the reason for that? Now you can go back to the SN1 reaction. This kind of mechanism, let's see if we'll see later, this kind of mechanism will follow the formation of the carbocation. And for the order of reactivity of carbocations, the order of reactivity of alcohols will follow for that of the formation of your carbocations, wherein you have your 3 degree, 2 degree, 3 degree alcohol is more reactive than 2 degree alcohol than your 1 degree alcohol. If you review on chapters 3, I think chapters 1, 2, 3, 3, no, chapters 3, you will see that 3 degree alcohol again is more reactive. Like for instance, no, this kind of reaction will have to follow this one. No, the 3 degree is more reactive than 2 degree, than 3 degrees more reactive than 2 degree than 1 degree. Okay, and the conditions because of this reactivity will be much harsher for a 1 degree than the 2 degree and a 3 degree, because we know that 3 degree is very reactive compared to a 1 degree. And for the hydrogen halides, the order of reactivity is that your HI is much more reactive than your HBr, than your HCl. And the reason for that is that their HI is more polarizable. The iodide of this is more polarizable than your Br, than your Cl. Now, if you have your sodium halide, in the presence, try to react that with alcohol, there is actually no reaction. Now, this one is the sodium halide would produce a halide in water. You will produce actually a basic solution, and with that, it's hard for your OH to leave. OH couldn't simply leave the substrate, and because of that, there will be no reaction because OH is a poor living group unless it is protonated, and the only way for this to be protonated is to napako. Wala na ko. Please tell me. Okay, the only way for this to be protonated is by the use of an acid. So here, if you use a sodium halide reagent, it's actually produce a basic solution. Like you will have your basic solution. So basically, you couldn't protonate or ROH, your OH here using this one. So the only way for us to proceed with the reaction is you always simply have your HX. And if you don't have your HX, then you can use your, you can use your PBr for bromine and SlCl2 as your source of chloride for your chlorine. And PBr3 is your source of bromide for your formation of alkyl bromide. But never itong sodium halide. The reaction would simply wouldn't occur. Okay. As I mentioned, OH is a poor living group. In this kind of condition, the reaction simply wouldn't be feasible. And the only way, as I mentioned earlier, the only way for you to proceed your Rx is for this first to be protonated, And for this to be protonated, you need to have your HX, not your sodium X. Again, this one will produce a basic or initial solution. Let me see. So for the mechanism, actually for this kind of reaction, it's just a repetition. A few minutes left. It's just a repetition for what we have learned with our SN1 and SN2 reaction. This one will record then. Okay, record. The reactions of alcohols actually is a repetition of what you have already learned with your SN1 and SN2 reaction. So you already have your knowledge actually for that. To proceed, you can only just use either the SN1 or the SN2 mechanism. So again, secondary, tertiary, allylic, and benzylic alcohols appear to react by a mechanism that involves the formation of your carbocation. So tertiary allylic, so benzylic. I think I have already mentioned the allylic, benzylic alcohol, And those are once you form your carbocation, your allylic carbocation and benzoic carbocation, your tertiary carbocation, secondary carbocation, actually produce a very stable carbocation as compared, and then you can, if you follow the SN1 reaction, then you can actually, once you form your carbocation, can easily be attacked by the nucleophile, forming a new product. So the step one is always the protonation of your alcohol. Once you protonate your alcohol, how does that happen? Of course, we use the electrons from the alcohol to obstruct a hydrogen from our hydronium ion. So, as nagigitan ng hydronium ion, the hydronium ion comes from the acid. Okay, in some other books, they just show the H plus, but know that H plus is always elevated with water, so you always have your O, H, your H3O plus. And where does this come from? This comes from your strong acids. No, your strong acids will always, for example, HCl, H2SO4. In water, they dissociate to completely to form your H plus and their conjugate an ion. And once you have your H plus, of course, they're solvated in water and you get your H3O plus. So first step is the protonation step of your alcohol. And we use the electrons. Let's see, we use the electrons coming from oxygen to obstruct the hydrogen. And once we obstruct that one, the electrons coming from hydrogen and oxygen would go to your oxygen. Okay, and you'll liberate water, the neutral form, and then you form your protonated alcohol. This one is fast. And this is the same mechanism actually that we have heard in SN1 and SN2. Once you have your protonated alcohol, this is the slow step, then the living group will now live to form your neutral molecule and produce your carbocation. Once you have your carbocation, of course, your nucleophile, the atom or group of atoms that contains an electron, can now attack an electron-rich substance, our electrophile. No? So the nucleophile, which is electron-rich, can now seek an electrophile, okay, to attack, and then you produce your new compound. This one is fast. Once you have formed your carbocation, the next step will then be very fast. So since this one is a step that's very low, this is our loading ko. This will become our rate determining step. Okay. Okay, so where am I? So this one is actually the mechanism, the application is actually the mechanism of the SN1 reaction. For the SN2 reaction, okay, first you have your protonated alcohol. Of course, once you have your protonated alcohol, it's a simultaneous backside attack of your nucleophile. Like here, can protonate, it can obstruct your carbon, bearing your protonated alcohol, and then the water will then leave to yield your water. So this is the SN2 mechanism. It's simultaneous attack. And of course, do not forget to remember on the conditions of the SN1 or the SN2 reactions and the mechanism behind the two reactions. Again, it will always come out, and those are the basic reactions that will follow, regardless of what our substrate would be. Like this case, our substrate is our alcohol, and whatever our nucleophile will be. Once we follow the substitution reaction, we always follow the same mechanism, whether it's SN1 or the SN2 reaction. So in this case, our substrate is always alcohol, since our chapter is on alcohol. Okay, so reactions of alcohols PB3, you can have your 1 degree or 2 degree alcohol, you can have your source of bromide from your PB3, and you can actually substitute your OH with your PB3. Okay, so the reaction does not involve the formation of a carbocation and usually occurs without rearrangement of the carbon skeleton, especially if the temperature is kept below. So this doesn't follow, whenever you use the PBr3, it doesn't follow the formation of the carbocation. So reactions of alcohols in PBr3, how does it happen? So phosphorus tribromide is often preferred as a reagent for the transformation of an alcohol to the corresponding alkyl bromide. So the mechanism, how would that be? First one is you have your PBr3. So your bromine here is the one that would bear the partial negative charge between phosphorus and bromine. And okay, and so if you have it is it would collide with alcohol, what will happen is that the electrons, oxygen being an electronegative atom and being an electron rich, will attack this phosphorus here, which is partially positive relative to your bromine, no? Because bromine will be the partial negative charge. So when there is an interaction, and this kind of interaction, we use the electrons coming from oxygen, you form a bond. So what happens once bond is being formed, then the other atom would have to leave. And of course, you will have your PBr2 minus this one. And since oxygen now would have 3 bonds, becomes protonated, passively charged,